So I'm going to do this both ways. So I'm going to start with randomization. So we're going to do the randomization, which is a simulation method using StatKey. So if I go to StatKey, I'm going to look down at the bottom in the more advanced randomization tests. And in this case, I'm looking for the chi-squared goodness of fit. I'm going to click on that one. And then I need to edit the data because this is an example that I got from Twitter. And so I'm going to change these to match Sean's data. All right, so here we go. I have my data. I've got the counts for each of these categories. I've got the same chi-squared statistic that we computed, which was 0.333. And now we're going to create a randomization sample. Basically, we're going to assume that you would get all of these sauces with the same probability. And we're just going to do random draws until we have 33 of the draws. So if I generate one sample, just randomly, I could get 7 Diablo, 11 Fire, 7 Hot, 8 Mild, and that would come out to be a chi-squared statistic of 1.303. Could do it again, and now I get a chi-squared statistic of 9.546, and again, or I could just get lazy, hit the 100 samples button, or really lazy and the 1000 samples button. So this is a randomization dot plot of the chi-squared statistic. And if I wanted to know how strange my observed value was, I could look at where 0.333 fell in the distribution. And with the chi-squared distributions, whether they're randomization distributions or the theoretical distribution, we're always looking at the tail to the right. So I'm going to do a right tail, and I'm going to substitute in, instead of this 9.546, I'm going to put my observed 0.333. Okay. And my p-value is enormous. It's almost 1. If the null hypothesis were true, it would be extremely easy to find something as extreme or more extreme than this. So this is very consistent with the null hypothesis, so we can't reject the null. So our p-value is 0.99. So we fail to reject the null. We do not have evidence to suggest the proportions are different. So that's using the randomization approach. But we could also do this same thing using a theoretical distribution called the chi-square distribution. And as always, if we're going to use a theoretical distribution, there's always conditions we need to check. For the chi-square distribution, we want to make sure that each of the expected counts is at least 5. And then if that condition is true, we're going to find a p-value as the right tail of the chi-square distribution. And we need degrees of freedom. So the chi-square distribution just has a single parameter for degrees of freedom, which is the number of categories minus 1. So you could think of that as k minus 1. So let's do this for the Taco Bell example. So we've got our degrees of freedom, that's k minus 1, and we had 4 categories, so 4 minus 1 is 3. So I'm going to have 3 degrees of freedom. And I should make sure that my conditions are met. Let's go back and look at my data. All of my expected counts are greater than 5. So I'm okay to use this theoretical distribution. And now we're going to go back to StatKey, on StatKey, and I'm going to go to theoretical distributions, and I'm going to pick the chi-square distribution. So that's the one with the fancy X. And like many of the distributions, it immediately asks me for my degrees of freedom. In this case, that's 3, and I say OK. So here's what my chi-square distribution looks like. And then again, I'm going to do a right tail, and I'm going to change this 9.348 to be 0.333. That's what we found. And there's my p-value from the theoretical distribution. So my p-value is 0.954. And again, we're going to fail to reject because we have that huge p-value. So once again, we do not have evidence to suggest that those true proportions are actually different. Okay, so let's just do a little bit of a recap. This is the set of steps for hypothesis testing, and we're thinking about, for chi-squared for goodness of fit. When we state the hypotheses, the alternative is always at least one proportion is different. When we calculate the test statistic, we're finding chi-squared equal to the sum of the observed minus the expected squared over the expected. So we don't have to find like a standard error or anything like that. When we're finding a p-value, we could use a randomization distribution, or we could use the chi-squared distribution with df equal to k minus 1. And we need to check all expected counts greater than 5. And then, of course, we're going to interpret the p-value in context. So this is inference for more than one proportion using the chi-squared test for goodness of fit.